Alright, hey, welcome back and welcome to Class 9. And in this lecture we're going to talk about some more bash concepts, something called pipes. And we're going to look at input and output streams, things called standard in, standard out, standard error. And this is one of the things that makes bash such a powerful environment to work in. Yeah, there's thousands of bash commands, but even if we learn only, a handful of bash commands, we can put these commands together in ways to make them work with one another and be able to do things without knowing an explicit command for doing what we want. So let's hop in here to a bash shell on the Linux server. And we know that if we pick a command like date, we just say date, hit enter, it somehow prints the current date and time on our screen. And if we do a command like BC, which is a calculator program, and we say something like 2 plus 3 and hit enter, it somehow ingests or reads this set of characters I typed, 2 plus 3, and it prints out a 5. And so we can communicate with programs. Programs can communicate with us. And we normally think of output coming to the screen and input coming from our keyboard, but that's not exactly how we should look at this. There's actually these things called streams, and two standard streams are standard in and standard out. And if we have a program, usually, not always, but usually our program will read input from standard in and generate output to standard out. And kind of by default, standard in means our keyboard, standard out means our display. So we could look at the date program and we could describe it as saying it takes the date and time and outputs it to standard out. Or we could look at that BC calculator program and say it reads expressions from standard in and produces the answer to standard out. But if we think of this as the keyboard and this is a display, that's what we've always known these commands do, right? We know that when we say date, it's just going to display on our current output screen the date and time. But we can work with standard in and standard out and have them be things other than the keyboard or the display. So one example of that is, for example, I'm in a directory with just a couple of programs in here. If I say date and I say greater than sign and I say some file, I no longer see the result of that date command. It figured out the date and time and it did its output to standard out, but it did not show up on my display. Instead, it showed up in a file, in particular the file that I named right here. And if I cat some file, it's got the output of the date command in it. And if I do, date, and I put it into another file, right, I have a new output file called another file. And if I look at that, it's got the result of that date command. And these are just plain old files, right? They're just collections of characters. I could have typed this and it would look exactly the same. But this lets me capture the output of a command and save it in a file. And so this greater than sign, we say that that's a output redirection, and we're redirecting standard out to go into a file. So if I do date greater than some file a few times, and I look at some file, it's only got the result of this last command. If this file already exists, it's zeroed out before the output of date is sent to it. But if I do a pair of greater than signs, so if I say date greater than some file, each time that I do that, and then if I look at the contents of some file, I can see that it's been appending the output of this command. So the double greater than sign means append standard out to this file. And if this file doesn't exist, it'll get created, and if it exists, it just tacks on to the bottom of it. So we can run a command and save the output. And standard in, we can redirect from, instead of reading from the keyboard, we can read from a file. And there's nothing magic about the date command. So for example, I have a main program, main.c, that prints a couple of lines of output. And I can compile that and run it. And it generates output. If I run that, and I put the output into, file.txt, for example, I don't see these two output lines on my display, but I have a file called file.txt that captured that output. So this works the same way on input. So let's take another program, let's call it main2, and main2 just does an fgets to read a line of input, and then it says you typed, and it tells me how many characters were in that line I typed by using the string length function, and I'm printing it out with a %LD because string length actually returns what's called a long integer, not just a plain integer. So I can compile this, and if I say main2, it says type something, hello there, and it says you typed 12 characters. Alright, so I have a file here. Let's pick a good file. I have this file called another file, which has this one line in here. I could say main2, and I can say less than another file. And instead of reading from my keyboard, when it reads from standard in, it will read from this file, and it will read the contents of that file, and it says you typed 32 characters. And if I look at another file, sure enough, it tells me this file is 32 bytes. It's got 32 characters in it. So I'm using the same old fgets function that we've used since 121, and it's reading from standard in. And this third argument we always put on fgets standard in, that's what we're doing. We're saying we want to read from this standard input stream, which is normally the keyboard. But if we run our program and we say program less than file name, then standard in means read from this file. So let's look at a slightly more involved program. Let's look at a main3, and main3 is almost the same thing, but I have a loop. So basically I'm going to prompt the user for input, read it in with fgets, and then I have a loop which says, well, that input is not the same as the string bye\n. Remember, fgets adds a new line to the end of your input, so I'm doing this as long as my input is not by\n. And in that case, I'm going to say, you typed, and echo out what the person typed, and then say length equals and show how long that string is. And then I'll, prompt them again, get another line, and go back to the top of my loop. So this is my main loop, and this is the usual trick we see in C with loops, is that sometimes we have to do our initial prompt and input before the loop, and then inside the loop we do it at the bottom. So this is an easy way. If the first time the user types something in, they say bye, this loop will never execute. Otherwise we get their input at the bottom of the loop and go back up to the top. And then when the loop is finished, the program will just say goodbye. Alright, so let's compile this. And if I run this, I can say, hello, and it'll say you typed hello, length equals 6. I can say cool, you typed cool, length equals 5. That is all, you type that is all, length equals 12. And then when I say bye, uppercase, it says goodbye. Alright, so that was reading from standard in, right? Because remember, my fgets is reading from standard in. And in this case, standard in was my keyboard. But let's change this to read from a file. So I'm going to make just a file, and I'll say hello. This is input from a file. What is happening? That's all. And then my last line will be BYE. So I've got an input file like this. And if I cat file, right, there's what's in my file. So I can run my main3 program, but instead of just saying main3 enter, I'm going to say less than, and I'm going to say read from file. And now standard in means read from that file. And when fgets tries to read in a line from standard in, it will read the next line from this file. When I do this, you could say it says say something, and that was the prompt, and then it says you typed hello, length equals 6. You type this as input from a file, length equals 26, all the way up to the last time that I typed bye, and then it just said it's goodbye. And if I wanted to, I could take the results of this and redirect it into a file called output. Now when I run the program, I don't see anything at all, but if I look at this file output, it's got the output that normally would have gone to our screen. So we can use greater than, less than in that way, and we can use two greater thans to redirect, but also append to the bottom of the output file. Alright, so this is a useful way to combine commands and get them to work together for us. So for example, we've played with the cow say command. We can say cow say hello, and we get a talking cow that says hello. So suppose we wanted a cow that would tell us what the current date was. We could say date and put that into a file, and then we could say cow say less than file, and the cow tells us the current date and time. But you know, each time we do that, it's telling us the same date and time because the contents of this file never changes. But there's another concept in Bash which is called piping. And we can say command 1 and then make a vertical bar which is called a pipe, and command 2. And what this does is it takes standard out of command 1 and standard in of command 2, and it connects standard out to standard in. So if I type two commands with a pipe in between, the first command will get executed, the second command will get executed, but the output of the first command will be fed to the input of the second. So for example, I could say date pipe into cow say, and now the cow tells me what the date is. I can say ls pipe into word count, and I can see that there's 11 lines produced by the ls command. And I could take that output and I could put it into cow say, and now my cow tells me the output of the word count command, which tells me there's 11 lines of output produced. So we can put commands together, right? I can say df to see my disk file system and pipe that into cow say, and my cow will tell me how much disk space I have on my different disks. I can do if config and see how much network activity there is. And if I do a search for GB, so grep is the way we search for something in a file. If I say show me every line of standard in that contains GB, I'll pick up this line and this line. And so if I do that, I get just these two lines of output. And if I want to keep a track of how much data is being transmitted, I could take this and I could pipe it into grep tx, and I get that single line, and I could put that into cow say, and now my cow tells me how many bytes I've sent from this computer. So this piping is really powerful, right? It lets us take the output of one command and feed it to the input of another, and we can do that without having to make intermediate files. And that's a really powerful notion, right? Because for example, if you want to know how much disk space you have on a particular partition, I could do df. Let's say I just want to know how much space is available on my boot partition. I could say df, and I could search for the word boot, and there's, you know, my partition information. So this is something we'll do a lot of, right? And we need to experiment with it and practice with it to get better at knowing how we can put commands together. But once we start to think in those terms, we'll usually find a lot of opportunities for combining commands to do more complex operations than we might otherwise be able to do. And this also works with variables. So for example, you know, if I type date, then that shows me what the current date is. If I type date and I put that into a file like out, then my file contains the output. If I say date and I pipe it into a command, then this command on the right executes on the output of that first command. Now if I say something like, you know, today equals date, and I echo the value of today, I just get the word date. Because remember, these assignments with equals in Bash are very literal. But I can do today equals $parentheses date, and this does something very different. This will actually run this command, capture the output, and in this case set today equal to that. So if I do that and then I echo today, it's the output of the date command. And you know, if I put a command in here that doesn't exist, this gives me an error. It says, hey, I tried to execute this command and, you know, I wasn't able to. That command doesn't exist. So we can capture the output of commands by using this $ parentheses notation, and we'll play around with that a lot in the practice problems. All right, I also want to talk about wildcards. For example, I've got several .c files in here. I could say more *.c, and it will do more on main2.c, and then it will do more on main3.c, and then it will do it on main.c. Or I could say vi *.c, and it edits main2, and when I say :n, it edits main3, and when I say :n, it edits main, and that's it, 3 files. So this asterisk is a wildcard, and it says, you know, match any file with the name anything followed by .c. And if I wanted to find, you know, all the files that have just an E in there somewhere, I could say list *E*, and it just shows me files that have an E somewhere inside their name. This wildcarding is really powerful, but it's a lot to ask developers to make each of their programs understand wildcards. And in fact, the ls program does not understand wildcards. It is not seeing an asterisk E asterisk when I say ls *E*. What's happening is that bash itself, the shell, is handling these wildcards. So if I say something like, you know, echo quote *E*, my echo statement shows me *E*. But if I echo this without quotation marks, my echo statement shows me a list of files. So in bash, anytime that we see something like this on the command line, before the command is executed, bash looks for files that match this pattern, makes a list of them with spaces in between, and then it runs whatever command you specified with all of this as the set of command line arguments. So if I say something like, you know, vi *.c, when vi, the program, starts to execute, it's going to see on its set of command line arguments 3 things: main2.c, main3.c, and main.c. Right? Vi doesn't have to know how to deal with this asterisk. It only needs to know how to deal with multiple entries on the command line. And this also works with variable assignments. So if I say x equals *.c, and then I echo $x, I can see it's equal to this list of file names. Now if I go into a different directory and I say x equals *.c and I echo $x, it's just *.c, because in this directory I don't have any files that end with .c. So this very much depends on what directory you're sitting in. And so this is a easy way to write programs that can accept wildcards in their argument lists without having to actually do any parsing of these wildcards. And asterisk matches anything, and a question mark matches a single character. So if I say ls and I do 4 question marks, this will show me all my files with exactly 4 characters in the name. And you can combine these and so on and so forth. Alright, let's look at functions in bash. We're going to do a separate lecture on functions in a couple of videos down the road. But let's just look at how we can take a set of statements in bash and put it into a function so that we can call it multiple times. So let me look at a bash script called looper. So looper, right, just sets a counter to 0, and it iterates until that loop count is equal to 11, right, no longer less than or equal to 10. So I'll echo the current value of my loop variable, I'll add 1 to it. This will run in a loop until loop count is not less than or equal to 10. So this is a bash script, and if I just run looper, it just prints out the numbers from 0 through 10. And let's suppose that for some reason that's a really useful thing to do. That's something that our program needs to do multiple times. So we can take this and we can put it inside a function. And so I'm going to say something like function do loop. I'm going to put a curly bracket, and I'm just going to indent the body of this. And now I have a function named doLoop, and anytime I execute it, it's going to do all of this stuff in here. And if I run looper, it doesn't do anything, right? Because I defined a function, but I didn't execute it. But at the bottom, I can say doLoop. And now when I run looper, it does my line of output. And if I call doLoop 5 times, it generates 5 lines of output. So this is a really easy way to take a set of statements that we might want to execute more than once and put it inside a function. In this case, my function is called doLoop. And then anywhere that I type the name of that function, it will go ahead and execute all of these statements, including executing loops and conditional statements and whatever else I put in here. Now, it's also useful to be able to pass values to these functions. And passing a value to a function is just like passing a value to a script. If I were to say something like doLoop 10, or doLoop 17, or doLoop 5, or doLoop 35, or doLoop 11, right? Inside here, I can get the value of that argument by using the symbol $1. So $1 always has the value of the first argument. So instead of looping while I'm less than or equal to 10, I could say, well, less than or equal to $1. And now if I run looper, each of my lines of output goes a different amount, 10, 17, 5, 35, and 11. So I've written a general purpose function called doLoop, and I can just say, you know, how many times I want the loop to execute, and it goes ahead and executes this set of statements, but with this variable $1 equal to, you know, whatever this argument was. And I might make this a little less mysterious by doing something like this: loop limit equals $1. This is the last value that we want to output, and then down here, instead of saying, well, less than or equal to $1, I could say loop limit. And this does exactly the same thing, but the code is a little more meaningful, right? I've got a loop count I initialize to 0, and I iterate as long as loop count has not exceeded loop limit. And up here in the beginning, I just set loop limit equal to $1. So that's an example of a function. The other thing that's missing from here is how we get a return value back from a function. And so let me make a different program, and let me call this function magic number. And I just want this magic number to just generate a random number. Now we know we can do that with just $random, but imagine we're doing something else in here. So I'm just going to say echo $random, and I'll go ahead and put that in quotation marks. And that's a function, right? It's going to output this random number. And if I execute that function, it doesn't do anything because we've declared a function but haven't run it. But I can capture the value of that function as follows. So let me just go ahead and run this first. I can say magic number. And when I run this, magic number says, you know, output a random number. But I can capture that by doing the following. I could say, you know, result equals $parentheses magic number. And then let's print out the value of result. And now when I run main, it tells me result equals, and each time I do this, I get a different number. All right, so what's happening here? This $parentheses says execute the thing in between the parentheses, magic number. So it calls this function. And this function prints out, to standard out, a random number. And since I'm taking the result of $paren and saying store that in this variable result, result is set equal to whatever this output. And then when I look at the value of result, it's just whatever was printed by our function. So I could add some other output here. I could say generating random number, and then I could say done. And so if I run this, it tells me result equals generating random number, this thing, done. And let's just make sure this is actually the value of the variable. Let me add some angle brackets, some delimiters around here. So I'll print out result equals angle bracket, the value of result. And now when I run this, yeah, sure enough, result equals, and all the stuff between the angle brackets, that's the value of the variable result. So result is a sequence of characters that includes new lines. So we can send values to functions and pick them up by using $1, $2, and the usual things like $number and so on. And we can get values back from functions by simply echoing them and then calling the function with this $parentheses notation to say capture what is sent to standard out. So we can use these functions to be general purpose chunks of code for us, and this is part of what we call modularizing our code, breaking it into modules. And one of the keys to programming is taking a problem and breaking it down into smaller pieces. This is why programming is a life skill, because it teaches you how to think about complex problems, not, looking for the magic solution that you learned many years ago or hoping that you stumble across it, but how to logically break down a complex problem into simpler problems and take the solutions to those simpler problems and put them together. Right? That's the essence of programming, and that's the essence of most complex problem solving. So how does that apply to writing a program? Well, let's say you're writing a program that's supposed to, play a game. Well, you can break that task into a number of pieces. You have to control the player's movement. You have to control the movement of an enemy. You have to display the background of the game. You have to update the background. Maybe things are happening, counters are expiring or experience points are going up, and you have to manage that. You have to display that information and so on. Each of those is a sub-problem. So you don't just sit down and you start writing a game from scratch. You break it into pieces and you say, okay, I'm going to work on the first piece, which is controlling how the player moves. Well, you don't just sit down and write that from scratch. First you say, okay, I'm going to pick up, AWSD, and when the person types W, I want them to move forward, and when they type D, I want them to move back. So first you just work on a piece of code that can capture those keystrokes. And you develop that, and you build it in a way that other pieces of code can use. And then you develop another piece of code, and you say, okay, this is the code that moves the player forward or backward or left or right. And once you've got that working, now you put those two pieces together. And you can type WASD on your keyboard and move the player around. So this idea of modularizing our code is going to be key. It's going to come up throughout this course and all of the other courses in the programming sequence. And one way that we modularize is by breaking things into functions. All right. There's another way we can do this. So let me go back to our looper code. And we had this thing, this function do loop. And our main program, for some reason is interested in doing this looping. Well, we have all of this stuff sitting inside our main program. That's kind of confusing to look at. So let me do the following. Imagine that I could just say do loop without having to put in all that definition for what do loop is. And let's save that as main. All right, so here's my my main program, and I just want to say do loop. So if I run this as is, it's not going to know what do loop is, because do loop is defined inside this file called looper. So here's what I'm going to do inside main. I'm going to add one line in the beginning which says source looper. So what does source mean? Source means open this file take each of the lines you find in there and execute them. It's kind of like a number sign include in C. It says take the contents of this and pretend that that file's contents is sitting right here. But this is a lot cleaner to look at, right? Source looper is just saying, hey, let's just, include that file and whatever functions are defined in there, like do loop, let's go ahead and define those. And so by just having that one extra line source looper, I can run main and it does what we expected it to do. But if I've already developed looper, and imagine looper is some very complex function that takes, a whole day to develop, I don't have to look at that code in here. I don't risk, damaging that code when I'm editing my main program. I'm just going to use it. So the source keyword is one way to do that. There's other uses for source, which we'll see in the problem set, but it's basically a way to execute something in your current shell instead of in a different shell. Alright, so that goes along with the idea of modularizing files. So this other notion of source is, for example, I'm sitting in my subdirectory called del. Let me make a script called bash. And let's say I want bash to switch my current directory to /etc. So I'll say print working directory and do an ls. Alright, so right now I'm in my home directory under this subdirectory called del. If I run my move command, I can see in the beginning it said that my current directory was /etc, and then it did an ls, and these are all the files that I find under /etc. So that program is supposed to move me into a different directory and then show me the files in there. But if I look, I did not actually change directories. I'm still sitting under my directory del. So what happened? Well, the basic idea is when I type the name of a script, there's a new copy of bash that gets started, and that copy of bash executes everything in here. So all of this changing into the etc directory and doing an ls, that was a different copy of bash that did that. The current version of bash that I'm sitting in right now did not do any of those things. So I could make another thing which says set x equal to this is fun. So if I execute move2 and I echo $x, it's got that old value from the last time that we tried doing this. So if I look at move2, I can try to confirm what x is equal to. I'll put an echo statement in there. And when I run move2, yeah, sure enough, x is equal to this is fun. But now if I look at the value of x, it's, star.c, something we did a while ago. So what's happening? Why is move2 not setting the value of x? Well, it is. But it's setting the value of x in a different copy of bash. It's like a whole different bash session gets started, executes these statements, and then that bash exits. And we're back to where we were. So if I want to actually execute those statements in my current shell, I can say source move2, and now if I echo $x, it'll say this is fun. And if I were to say source move, I'm currently in the del directory. I say source move, now I'm in /etc. And that's useful when you want to execute a set of statements in your current shell. And one example of that is when you want to edit that .bashrc file. You can make changes in there, and then you can say source.bashrc, and it'll execute them where you are. So that's a little bit about subshells and the source command.